what are we doing for time, Bob?
15.
15, good. We're doing good. There's a few practical things which we have learned over the years, and I want to share some of these with you. What you see here is the power production over several months. This runs from spring to fall. When do you think you'd have more power production, in the middle of summer or in spring?
Summer?
Huh?
Summer?
Summer. Well, you would think so because there's more sun. But solar panels don't like the sun. Well, that's not true. Because they don't like heat. And being in the sun means heat. A solar panel reduces its output for every temperature increase it gets. And some solar panels have a pretty good, what they call temperature coefficients, and some of them not so good. But typically, if we're talking about a temperature difference in spring and midsummer of 30, 40 degrees, that's significant. Look at this, what's happening here. This overall line from spring to August has a definite negative direction. And that's what's happening. You know, we're almost at 20 kilowatts a day in spring. And in mid-August, when we would say, hey, this is the greatest sun we can wish ourselves for solar energy, we're actually dropping almost 20%. So that is a practical piece of information which you should consider when you think about sizing solar panels for your own need. This is a picture of energy production, i.e. what comes out of the solar panels on a typical cloudy day. We have no days when we have no clouds. We may start with a blue sky when we wake up in the morning, but by the time it's 10, 11 o'clock, we'll see clouds appear. So this is typically what happens. Clouds coming, going, clouds coming, going, and you know the resulting energy curve is somewhere around here. So don't think that if you buy a 100-watt solar panel that you can get 100-watt power, because you're not. For one, a 100-watt solar panel will produce 100-watt at laboratory conditions, which is 76 degrees. Well, a solar panel in the sun is not 76 degrees, it's more like 110, which is where that temperature coefficient comes in. So you will never get 100. If you're lucky, you get 80. Lesson number one. This is in our Pacific farm a typical day of energy use. We're pumping water pretty much all day long, which is a good sized water pump producing 25 gallons a minute, and that's about 1300 watts. Then there may be some additional loads of tools and lights. At the end of the day, we charge our golf carts. We have 3 golf carts which run on batteries, and at the end of the day they need to be charged. So we plug them into the big battery bank and our energy consumption shoots up. At the end of the day the pool needs to be cleaned, so we start the big circulation pump. That's another 1000 watts. Boom, there she goes. The guys go and do all kind of stuff in their house which takes electricity. We have 6 full-time employees at the farm, and then by 9, 10 o'clock it starts tapering off and the lights go off and we go to sleep, and the next day it starts all over. So once you start making your own energy, you become very much involved. What happens to that energy? How do you use that energy? When do you use that energy? When should you not use that energy? What can you do to change that use to the point that you can optimize what you have? You probably cannot read this, but it's an example which I encourage you to do if you are interested, and that is to figure out how much energy do you use in your personal life, in your home, in your family. And that's simply by going from the top of the list, which says here a refrigerator, find out how much watts that refrigerator uses, and that's typically available on the little plate to the side or on the back of the appliance. Sometimes it says VA for volt ampere, which is the same as watts. Sometimes it will simply say so many amps, and you have to multiply that by the 120 volt which we have available. So a 120 volt fridge, which takes 1 amp, will use 120 watt. A fridge which takes 2 amps will use 240 watts, and so on. So step 1 is to identify how much power each item in your home uses. And then comes the most important decision: how many hours a day does that thing, that appliance, or whatever it is, unit, uses electricity? Well, the refrigerator is made to cycle on and off, and depending how many times you open it in the daytime, how much warm food you put in there, that changes, but as a rule, it runs about 1/3 of the time. Well, this guy was a little bit more conservative, so he said 10 hours a day. So his fridge takes 240 watts, and he says 10 hours a day, that's 2,400 watts to get his refrigerator going all day long. And we go to the next item, a well pump. Well, this is not a farm, so this guy says I'm only using it for an hour a day. So depending on your specific situation, you may not have a well pump. You go through your equipment, through your lights, your stereo, your computer equipment, your fax, your anything, your TV, whatever you have in your home which has a plug on it. And you add it all up. And you come with a number at the end of your piece of paper or your spreadsheet. And that's the number you're going to use to determine how many solar panels would you need if you were to change over to solar power, which is a question many people always ask me. And the very first thing you need to do is do this energy audit. How much energy do I currently use without making any changes? Just add it up, which is something we can all do without being an electrician. We can read the plates, we can add the numbers, and we come up with so many watts. Well, in our previous example, let's say we had 5,000 watts a day. I told you that in this part of the country we have about 5 sun hours a day in average throughout the year. So that means if I buy a 1,000 watt panel, 1 kilowatt, and I have 5 hours of sun, I make 5 times 1 is 5 kilowatts of power. And I'm there. That's my answer to my question. Well, they don't make 1,000 watt panels, but I can buy 10 panels of 100 or 20 panels of 50, whatever the case may be. And I'm ignoring the fact that these things are not 100% efficient. Let me remind you what we just talked about earlier. So we have to make some adjustments when all the calculations are done. But so here it says adjust for temperature and system efficiency. But I want you to understand the principle of how to make that determination without being an expert. The next question, if we are not on the grid, and I need to store the power for use at night and in the dark days of winter, how many batteries do I need? Again, this is something we can do without being an expert. We still have that number of 5,000 watts a day, which we need to store to at least get through one night and have 1 day of storage available. We assume a 12-volt battery. That's just an example. You may have 24. The numbers will change, but the answer will not. And our 5,000 watts are divided by the 12 volts to get the number of amp hours. Batteries are expressed in the time that they can generate current over so many minutes or so many hours. So it always says this is a so many amp hour battery. We would need, for our hypothetical example, 5,000 divided by 12 is 400 amp hour battery. Okay? There's a few ifs on batteries. Batteries don't like to be abused just like people or animals or anything that lives. Their lifetime is directly proportional to the times that we discharge a battery totally. If we kill our car battery 2-3 times, it won't take a charge anymore. It's just a very cheap thing made for starting your car, but it's not made to be totally discharged. The more industrial batteries, will probably do that 20 times. But what's important to know that if we discharge it only 80% or 70%, that number of times that we can discharge the battery goes up 100-fold. So as a rule, when we buy a battery, we need to consider the fact that we want to limit the number of total discharges in order to increase the lifetime, so we don't have to go to Walmart every 3 months and buy new batteries. So one good rule is to never discharge it more than half. Which doesn't mean you have to buy twice as many, but at the end of the day, you're gaining if you do the math. So another practical rule, batteries need to be rated at